Hello everyone, welcome back. In the previous video, previous set of videos, we started introducing the concepts of impulse, momentum, and the principle of impulse and momentum. And we have seen a bunch of examples how those principles can simplify some of the problems. One of the particular problems that are extremely well suited for this framework of impulse and momentum are those that involve something we call impulsive forces. First thing I want to be very explicit and mention here is that impulsive forces is a completely different concept as impulse. Note that impulse, we defined it is a physical quantity. We define it as integral of force over time. This is impulse. It has a very well-defined definition, concept in physics, in mechanics. Impulsive force, on the other hand, is more colloquial with looser definition, and it is absolutely unrelated to impulse. Well, very loosely related to impulse. And let's consider this concept of impulsive forces. And for you, I have an example of a golf ball and a club hitting that ball. And I want to study this system, and in particular, right now, let's focus on the duration of the contact. From the moment the club starts touching the ball until the ball is projected outwards. So let's analyze the forces acting on this system. Let me look at the forces on the ball with color red. Always I have the gravity, mass of the ball times gravity acting on it. In this cartoonish example, I have a normal force that is from the T on the ball. And during contact, there is some force F, let's call it F. And let's pretend there's no friction or anything. Just a normal force F from the club onto the ball. And let's analyze forces on the club. I have the reaction of that force, F, acting from the ball back onto the club. The club is being swung like this on the air. Ooh. So, well, club has some mass, so mass of club times gravity. And let's pretend there is some force from the shaft onto the club too. Let's call it P. And no friction. Let's assume simplicity. The club is in the air, only being swung with the force coming from the shaft, the club shaft. And I think that is all. Yeah, that is good for now. So let's look at, in this particular video, let's look at a bit of numbers. So in a regular, I don't know if it's a pro number or amateur number or anything, I don't know. So mass of the ball is roughly 45 grams. The mass of a club, in this example, I have, wait a second. Oh, my number doesn't make sense. I have 26 grams written here, but I have a feeling it must be 260 grams. Let's go with 260. It makes more sense, but maybe I'm wrong. 260 kilogram. Usually, if you measure it, the duration of the contact is on average between 0.4 and 1 milliseconds. Let's take an easy number. Let's go with 1 millisecond, so 0.001 second. And the average contact force hovers somewhere from 5 to 20 kilonewtons. 20 kilonewtons, yeah. So let's get some average number, 10 kilonewton, somewhere in the middle. Now let's calculate these forces. Force of gravity is, where do I do this? I didn't think it, I need more space. Okay, it's fine. So mb times g, let's take g to be 10, who cares, is 0.45 newtons. And mass of the club times gravity, let's do this, so you're not too mad at me, is 2.6 newtons. Normal force, it should be in the order of the same magnitude as this, mb times g. Force F, we know it, F this much newton, and P is, I think I took these from papers. Let's take it about 100 newtons. Now, finally, what I want to do is draw these forces as a function of time. So all these forces, force. Let's see, red one. The gravity on the ball is a very small amount, like this much, 0.4. Gravity on the club is also very small, 2 newtons, maybe this much. Well, maybe a bit lower. It's fine. The force P from the club is a bit bigger, 100 newtons. This is P. This is mcg. This is mbg. And to draw the force F, and these forces, let's pretend they are relatively constant, a little bit before to a little bit after the duration of contact. But the force F, the contact force, is 0. Let me draw it with purple. It is 0, it starts, this is the duration of contact. The force starts from 0, goes all the way up to maybe 10 kilonewtons up there. But for the sake of graphics, I'm going to break this. So do this, and then it comes down and becomes 0 again. Notice that the impulse, the area under curve, mind that this is actually that curve. This impulse is orders of magnitude bigger than the other impulses. So these, looking at the size of these values. So just for the duration of the contact, because the delta t is very small, the area under curve of each of these will be small except for force F that has a huge area under curve or impulse compared to all other forces. So long story short, the force F is what we call an impulsive force. Impulsive forces are those that have a very large value, but only exist for a very short period of time. In that case, if you have it during that short time, the impulse acting, the impulses, or the impulse of that force hugely dominates all other impulses in the system. And for this purpose, what we can do is consider the, oops, why is it doing that? I can consider the entire golf ball and the club as a system of particles. In this case, this force F becomes an internal force. And during that short period of time, I can essentially neglect all other external impulses in comparison to this internal impulse. And really the dynamics of the system during the short period of contact is only dominated by this internal impulse. And for all practical reasons, during the time that impulsive forces are active, the system let's do this. All external impulses, all external impulses can be safely ignored. In other words, if all external impulses can be ignored during contact, we can assume total linear momentum is conserved. So this is a very important result. It comes from the notion that just during that short period of time, all other impulses are small. The only thing that is happening and dominating the dynamics is that internal force, but that being internal doesn't affect the total linear momentum of the system. And during contact, you can safely assume the momentum is conserved. Obviously, there is a little bit of error because these other forces, the external forces like gravity and normal forces and force P and all of those exist, but their effects are so small that we can ignore it. And what we do generally in all situations that we have impulsive forces, if you look at the timeline of the events, pre-impulsive force, your dynamics is the same way as we had always been studying. For instance, you can use equations of motion to calculate accelerations or work and energy or any other forms to calculate movements. For a very short period, this is the duration of contact or impulsive force. You can go from before impulse to after impulse events using the notion of conservation of linear momentum. Conservation equation of linear momentum. Once you calculate what happens when the impulsive force ends, then you enter another regular regime. It is post-impulsive force. And again, you can use equations of motion, work and energy, or other forms of impulse and momentum principle to calculate what happens after. So essentially, you have this discontinuity. Physics is continuous, but you can safely ignore what happens during contact and go and jump from before to after and use conservation of momentum to make that jump. Okay, so that is, I think, all I wanted to say about impulsive forces and what happens during impulse. The only thing that remains is what constitutes, well, I gave you one example, that is the contact force, but what are other examples of impulsive forces? So in general, any force that is very large but short-lived is an impulsive force. Examples are contact forces, impulsive forces, explosion forces, like, I don't know, firing a cannonball or firing a gun or a fireworks explosion. Anything that is explosive in nature usually leads to these impulsive force effects. Forces that are continuously existing, like force of gravity or any other external forces, normal forces, and so on, those usually are not impulsive forces, unless something weird happens that I don't know. But yeah, anyways, the good examples are explosion and contact. If the force takes time to exist, probably it's not a good indicator of impulsive force. Okay, that is all I have. I think it turned out to be a long video, but that's fine. This is an important concept. I really wanted to take time to explain it. That is all I wanted to say. You'll see it's a very important and useful concept to simplify the problem. And we see a lot of examples in class. So I'll see you in the next video.